To begin with, we take the base integral and square it, and this lets us further transform the integral later. Next we expand the brackets, and as of right now both integrals are with respect to x. However, something to consider is that often the variable name within a definite integral is largely irrelevant, since by the end we solve for some real number and not a collection of variables. So with this in mind, we're going to keep the first integral with respect to x, but the second with respect to y. The integral can be written as a product of these two, and by using exponential laws we can claim the exponent further. And now we're left with the double integral with respect to x and y, leaving us a multivariable calculus problem. Trying to solve for this within the Cartesian plane is hard, essentially leaving us no better off than we were to begin with. However, by changing the coordinate system, this integral, which would otherwise be difficult to solve, is now much easier to compute. We can immediately convert the exponent by knowing that x squared plus y squared equals r squared. Next we take dx dy to be the area of Cartesian and convert it to be rd theta, which is the standard measure of the plane and polar coordinates. Finally, for the limits, we can see that in Cartesian, the limits represent all the values of x and y. So similarly in polar, we'd like the limit to reflect the entire plane again. So for our limit, we're left with 0 to 2 pi and 0 to infinity. Integrated in the integral, we can get minus 1/2 times e to the minus r squared, integrated between the bounds of 0 and infinity. Expanding this, e to the minus infinity becomes 0, and e to the 0 is obviously 1. So this leaves us with minus half, which then becomes a half. Half theta from 0 to 2 pi becomes half times 2 pi, which leaves us with pi. Finally, applying the root, we finalize a proof to give us the Gaussian integral.
So this is a geometric proof of Gaussian integration. It uses single variable calculus to find the volume of the Gaussian function, which helps to find the integrated Gaussian. So I've mocked up some Gaussian functions on the 3D plane in Python, which are going to be very useful to explain this method. So the first way to find the volume is by taking horizontal slices of this shape to form disks. We can then find the area of these infinitely thin disks. So as seen here, there'll be a disk, and they're all infinitely thin. We can then find the area of each of these disks, sum them up and find the whole volume. So the area of one disk will be pi r squared, since they're circles, and in this case the radius is just y. So the area of one disk can be given by AZ, and it's pi y squared. We can get AZ in terms of z by finding y in terms of z, and we do this by setting x equal to 0. We can then solve for y by taking ln of both sides, and then y squared is simply equal to negative ln z, and we can sub this back into the area of the disk function. Then we simply need to integrate this area between 0 and 1, since that's the height of the Gaussian. Start to 0 up to 1. Then we're given the volume here, which is negative pi times this, which is negative 1, and we end up with the volume as pi. So the next method to find the volume of the Gaussian is using vertical slices instead of horizontal slices. So instead of getting these disk shapes here, we vertically slice it, and we end up with shapes like this running along these lines all the way up that are infinitely thin. And again, we're going to sum up the surface area to get the volume of the whole thing. So these go off from negative infinity to infinity. So the equation here is each one of the surface areas of these vertical slices is given by the integration between negative infinity and infinity of e to the negative x squared plus y squared. Since we're integrating in terms of x, we can take out the e to the negative y squared term due to integer laws, and we actually end up with this term here, which is the Gaussian integral, which we're going to represent by I. So the surface area of each of the vertical slices ends up being e to the negative y squared times the Gaussian integral represented by I. Then we can go further down and sub this surface area equation into our volume equation. Again, integrating between negative infinity and infinity, and there it is again, the Gaussian integral, this time in terms of y. And we can go ahead again and sub in I, and the volume becomes I squared. Now this is the clever part, where we equate the two volumes since they're taking the volume of the same object. So the volume in the first method was pi, and the volume in the second method was I squared. So it becomes I squared equals pi, and then we can rearrange as I equals the square root of pi. So the Gaussian integral is equal to the square root of pi.
Hi, I'm Thomas Tra, and this is part 2 of the team assignment where I'll be covering another Gaussian integral proof, namely, proof of a change of variables using substitution. This time, we let j be the integral from 0 to infinity of e of negative x squared dx. Since x is used as a dummy variable, we can also let the function be equal to the same integral, only replacing x with y. Now similarly with the previous proof, it can be written as j squared, which allows us to apply some substitutions later on, which when simplified gets us a double integral from 0 to infinity of e of minus x squared minus y squared dx, in brackets, dy. Now in the previous proof we used multivariable calculus using polar coordinates in order to simplify the integral. This method differs a bit in that we need to establish 3 steps of substitution before continuing. First, let's set x equals yt in the inner integral, where y is fixed. We get this by equating t equals x over y, which becomes x equals yt when bringing over the y. In the same fashion, let's set dx equals y dt. And finally, 0 equals yt where t equals 0, and infinity equals yt where t equals infinity. Now let's substitute these steps into the integral, which becomes this, replacing dx with y dt and x with yt, which can be simplified down even further to become this, moving the y over and switching dy and dt. This interchange of integrals is justified by Fubini's theorem for improper Riemann integrals, even though e of minus y squared doesn't have an antiderivative. This function does, and simply just becomes a constant. From here, we can iterate as such. From 0 to infinity, and subbing in infinity and 0, which becomes the integral from 0 to infinity 1 over 2 multiplied by t squared plus 1 dt. And from here, we can apply this arctan rule to integrate as such, which becomes half tan inverse t from 0 to infinity. And from here, we just substitute infinity, which can be done by substituting a very large number, which becomes pi on 2, and 0, which becomes 0. And altogether, j squared equals pi on 4. And from there, we bring the squared over, square root this, which becomes j equals the square root of pi on 2. And that concludes my proof.
This proof uses differentiation and only single variable calculus, not multivariable calculus, to calculate j. Let j equals the integral. We're trying to differentiate j, and as this is an improper integral, for t is greater than 0 we set at equals this integral with a infinity equals j squared. Now we differentiate with respect to t using the fundamental theorem of calculus and get. From here, we want to change upper limit of the integral t into something else. We can use the substitution to let y equals xt. This will give us x equals ty. If x equals 0, then ty would equal 0 and y would equal 0 as well, as we know t is a big number and one of them has to be 0. If x equals t, then ty would equals t and y would equal 1 for the same reason. So we get this. At this point, we have to find its antiderivative, so we can change the integral and make it with respect to t, as find the antiderivative with respect to t would be easier than find the antiderivative with respect to y. Taking dt out of the integral, we would get. We can call this integral bt. From this, we know that a prime t equals negative b prime t. If this is true, then we also know that at equals negative bt plus c is true to anti-differentiation. So, now we can input a value into t before integrating. An easy value we can use is 0, because an integral from 0 to 0 just equals 0. By putting in t equals 0, we remove left hand side and get. Integrating this, we get negative 4 plus c, and c equals 4. And putting this back in the original equation, we get... In this last equation, if we let t equals infinity, then we'll get j squared equals 4. Therefore, j equals 2.
Thank you so much. I just have one very silly question. I saw that Brandon, I think the voice is coming from Brandon, but I saw in my Excel file that the group consists of Jack, Nicholas, Thomas, and Guyan. Am I right?
Yeah, that's right.
So I heard Thomas and I heard Guyan and Nicholas. So so Brandon, is he also in this group?
Wait, sorry, where's...
No, I'm also in this group.
Yes, Jack. Yeah. I already said your name.
Oh,
But
okay.
Brandon is Brandon Lau.
No, I don't see...
No, I'm not in that group. I'm not in that group.
Yeah.
So I think the voice came from your screen. So I was a little bit confused. So the 4 people that are listed in your team, okay, I just repeat: Guyan, Jack, Nicholas, and Thomas.
That's right.
Okay, thank you so much. Now, could you please maybe just, this is a comment. A couple of places you said e to the minus infinity equal to 0.
That's what it approximates to.
Yeah. So infinity is something that's not visible
Of
and
e to the
something
negative
that
x
you
squared
cannot
plus y squared.
feel or you cannot imagine also. It's bigger than what we imagine. It's larger than what we can expect. And it is like, something which is supremely far away from us. So when we need to apply, for a definite integral, say a to b, we quickly say, okay, put the top limit minus function at the bottom limit. We say that, very clearly and apply the a and b. But when it comes to infinity, it's not so clear. So what was your way of justifying this? So how do you substitute? You said, oh, put a large value. What is large? Large is relative. Just a comment,
Yeah, okay.
I want you to give me your impression of how you dealt with those challenges.
Like we really thought it was going to be exact and it was going to be an approximation at the end of the day. But yeah, we just took it to equal to 0 since it was really large, but
Yeah.
we accept that it wasn't going to be exact, but it was close enough for our means.
So did you search for any justification, like why it has to be 0 exactly? Why can't it be, so because exponential has got only positive values, it could be 0.000000 and then a non-zero quantity. So, in maths, we are so precise. Maybe in some other fields we can approximate, but in this case, there should be a legal way of mentioning it. So did you search for that, or did you try to get help, or was there any literature that helped you to overcome that difficulty?
We cross-checked with a couple different sources, but most of them seems to approximate it to 0 most of the time. I didn't find any example where it wasn't. If there was, I didn't come across it.
Mm-hmm. Yeah. Any other
That's right.
comments?
No, that's about it in terms of.
I think we cross-checked a lot of different literature and it all said the same thing. So that's why.
Sure. Thank you. Thank you very much for that. And but definitely not in the books, but in elsewhere.
Yeah.
Yeah. Okay. I just want to share something very quickly. I don't want time. I know that this is not a lecture time, but if you have got integral, say some finite number a, and infinity and some function, then this is technically a limit, not infinity. Okay, so limit as b so it's not like applying the number, so there is more intricacy involved. So you do the integral first and apply b, apply a, and then you get a finite answer in a and b. Then you will explore the possibility that this b is tending to infinity, and that's how you will look at this limiting process. Okay, so when you are in maybe high school level, then we say, oh, imagine a large number and then this. But afterwards, now you are at a stage where you could be using these concepts in your workplace and maybe more intricate situations. Then you need to look at some of the very classic textbooks where, okay, the integral calculation is not the problem, but this limit, whether it exists or not. Okay, so that is the question. So it boils down to the problem of existence of a limit. So I thought that I will share this with you so that you might be tempted to look further, and especially books. That's what I will recommend. Okay, and maybe grab some of those pockets of notes so that it can supplement to your learning. And if this question is asked in any of the interviews, then you are also prepared for that. And but on the whole, thank you very much. Any other comments?
I think we're good now. Yeah, thanks for watching, I guess.
Yeah. What type of challenges did you face?
Mostly, there were a couple of different proofs that we came across online, so we just kind of chose a couple that kind of flowed well into each other, just to have some sort of sense of clarity between the different parts. That was the main thing.
Yeah, I would say there was about like 20 different proofs for this. So it was kind of picking which ones are more relevant and explain it best, and we can use to explain best in a video.
Sure. And what are the criteria that you use to shortlist those 20 and converge to one proof that you liked most?
We kind of just use polar coordinates as like a basis, because it's the most popular proof for Gaussian integration. And then beyond that, we kind of discussed multivariable calculus, like J squared, mostly, and
sure.
Yeah, there are a couple of different proofs that are similar to each other, but differed slightly.
Yeah, I know for the geometric one that I did seemed kind of relevant to the course, with like graphing the 3D shapes and stuff. So that's why I chose that.
Yeah, I love that idea of using the Mathematica to actually visually show the slicing as well as the vertical cross sections. It's a good idea because when you have so much of technology available, you should use it. And also,
can I just point out, Osher, I think the student has coded that up in Python.
Yes, it was in Python.
So it's very commendable that they have done that. Yeah, it was very good.
Yes. Yes, really, I agree. I fully agree with that. And at a couple of places, I think Thomas was mentioning the existence of this integral. That type of wording is very classic. Please stick to that, because an integral is not something that that is so obvious. Okay, so we need to sometimes establish the existence of it. So which means you need to dig deeper for any theorem, relevant theorem, or a condition that that you can bring in, and then mention the existence. So not all of them exist. So I can create a very fancy integral, but whether it exists or not depends on lots of theorems. So it's good that you have taken up a very interesting project. So if others have no questions, I would call upon Max and Akarsha. Are you here? Okay, I don't think those two people are here. So I will call upon Matthew Cooper, Carlin, Brendan, Oates, Joanna, Hyunjin Jeong.
Yep.
So there are 5 in this group. So welcome to all of you, and my big clap for a